Good afternoon. Today I'll be presenting the quantitative analysis of flow characteristics and contaminant dispersion in urban canopies. The velocity and scalar contaminant data that we have used in this research has been acquired using magnetic resonance imaging techniques from Stanford University. This research looks into simple urban canopies and how flow and contaminant travels throughout this urban environment. Here we used a regular array of cubicle buildings and one central tall building. We compare two cases, one in which the wind direction is aligned with the streets and another which the streets are skewed at a 45 angle from the bulk velocity direction. This is a top-down view for both orientations, the red square indicating the tall building. Bulk flow travels in the positive x direction for this research, and the center of the coordinate system has been defined as the bottom center of the tall building. H, which is a length scale we'll be using repeatedly, is the height of the cubicle short building. The tall building height is 3h, which is 3 times that of the regular short buildings. We'll first start on by looking into the flow characteristics. To gain an overall idea of how the flow field looks like, we have created a color contour of the x direction velocity for both the 0 and the 45-degree orientation. The streamlines have also been released at the same height, which is y equals 0.5h, the mid-height of the regular short buildings. For the 0-degree case, we can see how the inlet flow travels throughout the boulevards in between the shorter buildings. However, for the 45-degree case, we see how the flow deviates a lot significantly from the direction of the bulk flow. In the first row of short buildings, we can see small vortices developing directly behind the buildings. And we can also see how the streamlines cross over the short buildings, so it travels upwards. The wake of the tall building also incorporates almost none of the incoming inlet flow. This is the color contour of the y direction velocity at the same height, y equals 0.5h. We can see that there's a lot more variety in magnitude in the 45-degree case. The individual short buildings develop an area of upward velocity, which is accompanied by neighboring regions of downward velocity, the regions of blue. However, for both cases, we can see similar characteristics for the tall buildings. We have a strong zones of strong downward velocity directly in front of the tall buildings as the incoming flow hits the front of the building. And we have a strong upward velocity developing behind the tall buildings for both of the orientations. We can zoom in on this downward and upward velocity a lot closer in this slide. So why does this area of strong upward velocity happen behind the tall buildings? We can attribute this to the chimney effect. The incoming flow hits the wayward side of the tall building and then is accelerated as it goes around the base of the tall building. Then this accelerated flow is sucked upwards towards the low pressure area and then travels back downstream in the direction of the bulk flow. We see this pillars of vorticity of this vertical axes vorticities developing in this area of upward motion for both the 0 and the 45-degree orientations. We'll now look into the contaminant dispersion. Here we have provided the same top-down view of the urban canopies, except here we outlined with a gray square where the contaminant injection point is. Note how in the 45-degree case, the injection point is in the positive z side of the tall building. The isosurfaces of the concentration of the contaminants show us how the contaminant starts out dispersing throughout the canopy. For both 0 and 45-degree cases, we can see how the contaminant starts creeping up the side of the tall building and then disperses more in the positive x direction, in the flow direction, as it seems to fill up the space of the separation bubble. However, in the 45-degree case, other than the contaminant does not only disperse in a vertical motion, but also in along the boulevards in the spacing between the short buildings. Here we have pointed that out with the red arrow in the bottom right image. Since the injection point of the contaminant is in the positive Z side of the tall building, the contaminant also disperses through the boulevards in the positive Z direction. This is a lot more evident in the isosurface of the contaminant at 3%. Here again with the red arrow, we have pointed out how the contaminant disperses not only in the wake of the tall building, as with the 0 degree case, but also in the positive Z direction down the boulevards in the spaces between the short buildings. We can attribute this to the fact that the flow within the boulevards is a lot slower in the 45 degree case due to the amount of obstacles, and unlike the 0 degree case in which this contaminant is swept out in the bulk flow direction, in the 45 degree case, this contaminant has a lot more time to disperse throughout these boulevards, and thus in the positive Z direction. This is a color contour of the contaminant at y equals 0.5 H. We can see again here how the contaminant really disperses in the positive Z direction in the 45 degree case, while in the 0 degree case, the dispersion is mainly behind the tall building and is obstructed by the short building that is directly behind. This is y equals h, so directly above the height of the short buildings. We can see how in the 0 degree case the dispersion is now unobstructed by any obstacles and is free to go in the positive x direction, the direction of the bulk flow. While in the 45 degree case, we can still see the remnants of the dispersion that happened within the boulevards. This is for y equals 1.5 H, and this is for 2H. Here we can really see how the dispersion of the contaminant has assumed the shape of the building wake. We have also did a simple stream tube analysis to see the importance of advection and turbulent dispersion within the urban canopy. Here we created a stream tube by releasing 1,000 streamlines from the perimeter of a circle encompassing the center of the contaminant release injection point. These streamlines were also computed using the mean velocity field measured using the MRI technique. So with these stream tubes, we computed how much of the concentration is contained within the stream tube. If the turbulent dispersion was to be low, then most of the concentration should be contained within the stream tube. So this is a graph that we had, and the graph shows that there's a lot more concentration contained within the stream tube in the 0 degree case than in the 45 degree case. Another thing is how the amount of concentration that is contained within the stream tube falls significantly after x equals 1.5 H. Now this, with respect to the rest of the building canopy, is directly after the area of strong upward velocity directly behind the tall building. So as we travel downstream, as we get past the region of strong upward velocity, the concentration is diffused outside of the stream tube, indicating that there is a stronger turbulent dispersion.